Differentiation is a method used to find the derivative of a function. In calculus, differentiation helps us determine the instantaneous rate of change of a function with respect to one of its variables. In simple terms, it shows how quickly a quantity changes at a certain point. Differentiation is widely used in real-life applications such as physics, engineering, and economics. For example, it can be used to calculate speed and acceleration, analyze business profit, and optimize design in engineering. There are 6 main techniques of differentiation. First, we have the constant rule. The derivative of any constant value is always 0 because a constant does not change. Second is the power rule. The power rule is used to find the derivative of a variable raised to a power. It is one of the most and commonly used differentiation techniques. Third, we have the quotient rule. The quotient rule is used to differentiate a function written as a fraction or ratio of the differentiable function. Next, we have chain rule. The chain rule is used to find the derivative of a composite function, which means a function inside another function. In addition, we have product rule. The product rule is used to differentiate a function that is formed by multiplying two functions together. Lastly, we have derivative of logarithmic, exponential, and trigonometric function. These rules are specifically used to differentiate logarithm, exponential, and trigonometric expression. In conclusion, differentiation is an important topic in calculus because it helps us understand and analyze change in many real-world situations. By learning this differentiation technique, we can solve various mathematical and practical problems more effectively.
For question number 2a, first of all, we let u is equals to sin x plus 3. Therefore, u prime is equals to cos x plus 3. Because based on the formula, sin x will become cos x, meanwhile sin x plus 3 will also become cos x plus 3 because this x plus 3 represents as x. Now, we let v is equals to tan u, and since v equals to tan u is a composite function, we need to apply the chain rule. V prime is equals to sec square u multiplied by u prime. Because based on the formula also, tan x is equal to sec square x. V prime will also become sec square u, then multiplied by the derivative of inner function, which is u prime. We need to substitute u equals to sin x plus 3 and u prime equals to cos x plus 3. Our v prime is equals to sec square sin x plus 3 multiplied with cos x plus 3. We need to differentiate both sides where dy dx is equals to d dx multiplied by 4x plus d dx. When we differentiate 4x, it will become 4. And what about the v square? By following formula in chain rule, d dx will equal to u to the power of n and is equals to n u to the power of n minus 1 multiplied by u prime. V square is equals to 2v to the power of 2 minus 1 and multiplied by v prime is 2v multiplied by v prime. Therefore, 4 plus 2v multiplied by v prime. Hence, the dy dx for this function is equals to 4 plus 2 tan multiplied sin x plus 3 sec square sin x plus 3 cos x plus 3. Move on to the next question, which is 2b. First, we need to let u is equals to exponent 2x minus 2x, v is equals to 3x plus 1. U prime is equals to d dx multiplied by exponent 2x minus d dx multiplied by 2x. The exponent 2x is a composite function. We need to apply chain rule. U prime is equals to 2 exponent 2x minus 2. When we differentiate exponent 2x, it will become d dx multiplied by exponent 2x and equals to exponent 2x times d dx multiplied with 2x. Therefore, exponent 2x multiplied by 2, since the derivative of exponent 2x is 2, v prime is equals to d dx times 3x plus 1. V prime will become 3. When we differentiate 1, it will become 0. Since given function is in a fraction form, then quotient rule is applied. The derivative of numerator and denominator are determined separately before substitute into dy dx equals to vu prime minus uv prime over v square. Then, by applying quotient rule, we need to substitute all of this to find the exact derivative of given function. dy dx is equals to 3x plus 1 multiplied by 2 exponent 2x minus 2 minus by exponent 2x minus 2x times 3 over 3x plus 1 square.
Hi everyone, next I'm going to guide you through solving question 3 using implicit differentiation. By looking at the question, our main goal is to find dy over dx. To make things easier, let's look at each term on the left side individually. For the first term, to y over x, we need to apply quotient rule because we have a fraction. Let's set our u as 2y and v as x. Differentiating this gives us u prime equals to 2 dy over dx and v prime equals to 1. Applying the quotient rule formula, which is vu prime minus uv prime over v square, we get the answer 2x dy over dx minus 2y over x square. Next, for the second term, x square minus 3y to the power of 4, we have a function inside another function. So we must apply the chain rule. We bring the power of 4 to the front, lower the power by 1 and then multiply by the derivative of the inside function. This gives us 4x square minus 3y to the power of 3, 2x minus 3 dy over dx. Finally, differentiating the right side, 5x cubed plus 2 is straightforward. It simply becomes 15x squared. To simplify this and make it easier to solve, let's clear the fraction by multiplying the entire equation by x squared. This removes the denominator from the first term and modifies the rest, giving us. Now we move to the algebra parts. We need to expand the middle term by multiplying 4x squared. X squared minus 3y to the power of 3 into the bracket. Multiplying it by 2x gives us 8x cubed. X squared minus 3y to the power of 3. Then multiplying it by negative 3 dy over dx gives us negative 12x squared. X squared minus 3y to the power of 3 dy over dx. So this is the full expanded equation. Next, to isolate dy over dx, this rearranges our equation into 2x dy over dx minus 12x squared minus 3y to the power of 3 dy over dx equals to 15x to the power of 4 plus 2y minus 8x cubed x squared minus 3y to the power of 3. Now we can factor out dy over dx on the left side. To get the final expression for dy over dx, we can just move the entire bracket to the denominator of the right side. And here is our final answer. Dy over dx equals to 15x to the power of 4 plus 2y minus 8x cubed x squared minus 3y to the power of 3 over 2x minus 12x squared minus 3y to the power of 3. To conclude, using implicit differentiation along with the quotient and chain rule is highly effective for this problem. So, my main recommendations to avoid careless mistake for this kind of question is that you need to write clearly and double check your coefficient line by line. That's all from me. Let's move to the next question.
Hi, I'm going to show the solution for last question, that is question number 4, which requires to use the linear approximation value to estimate the value of 4 square root 18.99 minus 2 over square root 18.99 correct to 3 decimal places. So first, let's look at step 1 where we define our function and k values. We can define the expression as function of x by fx equal to 4 square root x minus 2 over square root x. The given value we want to evaluate is x equal to 18.99. To use linear approximation, we need to choose a conventional initial value of x, that is x naught, that is very close to 18.99 and easy to calculate with a calculator. We choose x naught is 81. Next, we find the change in x, that is dx by subtracting x naught from x. Then we got minus 0.01. Moving to step 2, we need to differentiate our function to find fx. First, using the power rule, we bring the power to the front and increase the power by 1. Next, we substitute our chosen value x naught equal to 81 into the derivative function to find the rate of change at specific point. After calculating, we get 0.011. Next, in step 3, we calculate the estimate change in our function value, which is df. The formula is df equal to fx naught multiple dx. Then we substitute the value before earlier. Then we got negative 1.063 multiple 10 negative 4. Finally, in step 4, we approximate the total value using the linear approximation formula, that is fx equal to fx naught plus df. Let's look at f81. We substitute the value and we add our small change df to this initial value. Then we got 2.778.